Hi, welcome back. Or should I say привет? Меня зовут Anjana Vakil. I have been working on my Ukrainian the last few days. It's not good, as you can tell, but I am always looking for language tutors, so come find me later. You can find me on Twitter at Anjana Vakil. And that has links to all of my other online presences. I'm a software developer. I'm based in San Francisco, where I work for Mapbox on engineering, learning, and development. But as was mentioned, before I was into programming, I was into philosophy. And so I love geeking out about the abstractions, the mental models that we use to write and think about our programs. And so I really love thinking about programming paradigms and how they affect the code that we write and our experience as programmers. If you want to nerd out about programming paradigms with me, about functional programming, object-oriented, declarative programming, logic programming, whatever, come talk to me afterwards or check out a talk I have on YouTube called Programming Across Paradigms. And today I want to talk to you about two paradigms in particular. You might say that they're kind of star-crossed paradigms, that they're sort of competing in a way, at least that's how we think about them a lot of the time. And the paradigms that I'm talking about are iteration and recursion. Now, you might not think of these as programming paradigms. They're not typically referred to as such, but I think that they qualify because they're basically two different models, two kind of different abstractions or mental models that we use to take the same chunk of code and execute it multiple times repetitively. So iteration is typically associated, or we could think of it kind of as like a sub-paradigm, imperative programming, where we're telling the computer, do this, and then do that, and then do this other thing. And so in iteration, in this mental model, we are thinking about repetition in terms of loops. We're looping over our code using for or while, and as we go through in each successive run of that loop, we're changing things. We might be pushing things onto an array or changing a counter. And so we've got values changing over time, we've got state. So this is a stateful model for doing the same chunk of code multiple times. And I'm a big fan of having kind of a mental picture, something in the real world that I can associate with a model that I'm using to think about my code. And yesterday in Study Mira's talk, we had a little game of Guess the Movie. So I've also got a movie that I think perfectly captures what it's like to live in an iterative world. It's an old movie from the 90s with Bill Murray. Can anybody guess? Groundhog Day, bingo. All right, has anybody seen this movie? Few folks have. Okay, so if you haven't seen it, in Groundhog Day, Bill Murray is trapped in the same day. He's living the same day over and over again. Every morning he wakes up, the same songs on the radio, etc., etc., and he's kind of like in this infinite while loop. But he can remember things from day to day. He remembers that he's been there before. He can take a piano lesson every day and get better at piano, so it's really stateful. So if you want to watch a movie and feel like you're doing work, go watch Groundhog Day and be like, yeah, I'm studying iteration. What? All right, so that's iteration. What about recursion? So if iteration is sort of part of the imperative programming paradigm, recursion is kind of a sub-paradigm of functional programming, or it's often associated with functional programming. And here, instead of looping, we're repeating ourselves by self-reference. We're taking a function and calling itself. And in each call, we're not, as we were in iteration, we're not keeping things stateful and changing values over time. Instead, in each successive call, we're usually working with something like a pure function where we are only concerned with the current calling context. So we've got a stateless type of repetition here. Now, of course, there's a movie that this also reminds me of. Guess the movie. Inception, bingo. So, in Inception, in case you haven't seen it, Leonardo DiCaprio, Dreamboat, is and his buddies. They all are kind of like dream explorers, and they can fall asleep, enter somebody's dream, and then within that dream they can enter another dream, and then within that dream they can enter another dream, and so on and so forth. And so they're kind of recursively going through these dream states. And in each dream state, they don't really have access to like the dreams above it, so they don't even know all the time if they're in a dream or not in a dream, so they have to carry on a little top and like try to figure it out. Anyway, point is, if you want to pretend like you're doing programming work and watch a movie instead, you can watch Inception and tell your boss you're studying recursion. So, all right, so these two paradigms, iteration and recursion, They're both perfectly valid ways of approaching problems. They're two different models, and they have different qualities that make them better or worse for certain types of problems or certain situations. And one important way in which they differ is in their efficiency. So now, if you read people getting really up in arms on the internet a lot, that you might hear that people say like iteration is a lot more efficient. Well, I think it is, but only if we're talking about machine efficiency. So if we're talking about the constraints on the computer and the time and space that it takes to run our code, that's machine efficiency. And iteration is often more machine efficient, perhaps because it's a little bit more like how our computer thinks. It kind of thinks iteratively. Whereas we also have another type of efficiency that we need to think about, which is human efficiency. We are people, we are programmers, we're humans, and we need to write, read, and maintain our code, and that takes cycles on our human processors up here. So we've got another type of efficiency, and some people find recursion a little bit more intuitive to solving certain problems, a little bit more human efficient, as opposed to machine efficient. So we've got these two paradigms. They're different, but I would say they're equally valid choice. We might say that they're two paradigms, both alike in dignity. And we're at a JavaScript conference, so it's in fair JavaScript that we lay our scene. And if there's any English literature buffs out there, they might recognize these phrases, two households both alike in dignity in fair Verona, where we lay our scene, as the opening lines of, anybody? Shakespeare, Romeo and Juliet. So William Shakespeare's Romeo and Juliet begins with those phrases. So I am now quoting Shakespeare in a tech talk, and I've made two Leonardo DiCaprio movie references, and it's only a few minutes in, so I'm really excited about that. As you can tell, I love Leonardo DiCaprio. Anyway, I think Romeo and Juliet is also a good kind of model here, because often people get really up in arms, like pointing their guns at each other, like, no, iteration, imperative programming is more efficient, no, recursion is more elegant and better, like there can be only one survivor. But I don't think it has to be that way. I think unlike Romeo and Juliet, this story has a happy ending. And it's thanks to some really cool new-ish over the last few years features in JavaScript can allow us to take elements of one paradigm and bring them into the other one to make them both better to work in. So this is what we're going to be talking about today, is how we can use elements of iteration to make recursion better and elements of recursion to make iteration better. All right, so Act 1. What if we could have iteration, which is machine efficient, but make it more intuitive, make it more human efficient? Okay, we're programmers, so we love trees. And I've got a really simple little tree node here, where it's just got a value and then possibly a left child and possibly a right child. And I've got a little function, make tree, which is gonna take that node and turn it into a little tree that looks like this. Got some values in it. No big deal, simple tree. All right, if I want to iterate over this tree and get out, if I want to traverse this tree and get out all of the values in the tree, if I asked you to explain to me how to do that as a human, you might say something like, okay, start at the root node, tell me the value of that, and then if there's a subtree on the left, go through that subtree and tell me everything in it, and then if there's a subtree on the right, go through that subtree and tell me everything in that. If you described it that way, if we were talking about it, talking it through, that would be kind of a recursive approach, what you've just described. I might write it up like this. I have a recursive traverse function here, where first what I'm going to do is just log the value of a particular node. I start in with the root node. Then if there is a child node on the left, I'm going to recursively traverse that, starting with that as a new root, and then same on the right. And that's our recursive case. So every recursive function has some recursive case where it's going to call itself. And then we also need a base case so that we have a time where we stop recursing so we don't fall into this infinite dream state. We don't want that to happen. That would hurt Leo's brain, so we don't want to do that. So we need a base case. In this case, if there are no children on the left and right, then we're just going to return, and we're done. So if I run this on my simple tree, I get out the values as I would expect, and this seems, I don't know, do you agree? I think this is pretty intuitive. It's kind of how you would tell me how to do this, and so it's pretty human efficient. This is our recursive approach. Now, what if we were going to iteratively traverse this tree and find everything in it? So, one way we could do that is with a little function like this. First of all, if you notice it's a little bit longer, I don't know about you, but immediately looking at it, I have to kind of think about it a little bit harder. What we're doing is we're kind of using like a little to-do list, and we're putting nodes from the tree onto the to-do list, and then we're kind of taking the first thing off the to-do list, telling me its value, and then if it has children, we're putting those onto different ends of the list so that we get everything in the right order, and it works. I can run this code and it gets out all the values, but I don't know about you, but I don't find this as intuitive. I find this a little bit harder to think about. It was a little bit harder to write for me, and this is like an iterative approach, but it's not really that easy to work with. So, wouldn't it be great if we had more intuitive iteration? If we could just say, hey, for each thing in the tree, tell me what the thing is. That would be nice and simple. It would be kind of more intuitive. And we can, thanks to some cool, new-ish, well, you know, ES6, a few years old, features that we got in JavaScript that allow us to do more kind of custom iteration. So we've got iteration protocols, we've got iterables, we can define ourselves, we can use generators to define iterators to make things iterable, and then we can use a for-of loop to iterate over whatever kind of thing we want. So let's see what that might look like. So now I'm making a new node, a new type of node called iterable tree node, where I basically got my simple node in there, and what I'm going to claim is that we can make it better by bringing in the recursive approach that we had to iterating over the tree and making that something that we can access iteratively in our new type of tree node. We can do this by assigning an iterator to the simple iterator property, and we can build that iterator in the same exact recursive style as we were traversing the tree before using generators, using a generator. So we've got now this generator called recursive iterator, because I'm really good at naming things, where first we're going to basically output the value using a yield statement, and then if there's something on the left, we're going to iterate over everything in that left subchild and successively yield those values, output those values, and then the same thing on the right. So if you look at these side by side, you know, where instead of logging, we're yielding from this iterator, but it's the exact same approach. And then in our base case, if there's nothing on the left and right, we just stop iterating. So now we can just loop over our tree. I'm making the tree from this new type of node, and I can just say, for let val of better tree, tell me the value. And this works just as well, and in this case, it's more, I argue, more intuitive because it's more like that recursive approach that we wanted to use originally. So it gets even better now in ES 2019, and already in some browsers we've got async iterators and the generators that go along with them, so we can do this even better. So we've got these features in JavaScript now that allow us to take the recursive model, the more human efficient model that we want to use, and bring it into our iterative code. So with a little love from JavaScript and a little love from Recursion, we get more human efficient iteration. I don't know about you, but that makes my heart feel warm and fuzzy. So that's Act 1. How about Act 2? Now let's talk about recursion, but more machine efficient, more performant. All right, so because I love talking about Leonardo DiCaprio and his movies, so thinking about Inception, we have, you know, a dream within a dream within a dream within a dream. I'm able to say that because our human language also has recursion. We're able to, in a sentence or in a phrase, recursively build up a kind of nested phrase. So I can say something like a dream within 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 a dream, and I can keep going for as long as I want. That's a cool feature of human language. I also studied linguistics, so I love nerding out about that too. So, all right, here's a little function, which I've just wrapped in a little script, to output our dream within a dream within a dream phrase, given a number n of like dives that we want to do. Like, what depth do we want this dream to go? How far do we want to push Leo into the dream worlds? So in my base case, if n is 0, if I'm not doing any recursion, then I'm just going to return the phrase a dream. And if I am doing recursion, then I'm going to make a recursive call, decrementing n by 1. And then whatever the resulting phrase of that is, I'm going to add on within a dream to it. So if I run this little script with an input of 3, I get the phrase a dream within a dream within a dream within a dream. So I've got 3 within, so I'm like 3 dives here. Cool, all right. If I run it with 30, I get this long thing that I'm not going to say. And if I run it with 3,000, I get 30,000 withins. They don't fit on the slide, but you know what I mean. What happens if I run it with like 30,000? Stack Overflow. Stack Overflow. If I run this as written, I get this sad little message, maximum call stack size exceeded. Oh. I think in Firefox, you even get the message, too much recursion. Just too much recursion for you. You cut off. Too recursion, much sad. All right, and so this is heartbreaking, right? I have this recursion that I can write, I can talk about the problem in my code pretty intuitively, but I can't run it because of our stack. So what's the deal here? What happens when I run this code, and why does recursion not love call stacks? So okay, if I run my little script here with input of 3, I've got some finite amount of memory for my stack, and the stack has some of the stuff on it, you know, whatever global things it needs. But when it comes time to running this actual recursive inception function, first of all, I get a new stack frame for this call to recursive inception of 3. Now, the stack frame doesn't look like this to JavaScript. I'm a human, so I wrote it in something that's a little bit more human for me, so it doesn't look like actual JavaScript code, but this is just my way of helping me think about what the engine sees when it's trying to run this call. So it's calling recursive inception with input 3. It's saying that dreams is gonna make a recursive call to the same function but with a different input of 2, and then whatever that returns, it's going to add on within a dream. So this means I need to make that recursive call to recursive inception of 2. So I'm gonna add a new stack frame, which now has input 2. It's gonna make a recursive call to recursive inception of 1, which now has a new stack frame for it, and then this is going to call recursive inception of 0, so I need a new stack frame for that. Now I've hit my base case, right? So n is 0 now, so I don't need to make any more recursive calls, and q, because I've just come up against the limit of my stack. Now, in real life, it's a little bit more than like 3, but so now I can just return the phrase in a dream. That gets returned to the previous stack frame, which then adds on the phrase within a dream, puts that together and returns it to the previous calling one, and then that adds another within a dream, and that returns to the previous one, and that adds another within a dream, and finally we output our phrase, a dream within a dream within a dream within a dream. Is that the right number? It doesn't matter. Anyway, so this is what happens. So then, what happens when I do this with a larger input number, and I have to do more recursive calls? Well, you probably get the idea. We start out with a call to recursive inception of 30,000. That adds a new frame for a call to recursive inception of 29,999. That adds a new frame to 29,998, and so on and so forth, until eventually I don't have room to put the next frame on the stack. Now, again, it's going to be after a few more than 3, but still, there's going to come a point where I just can't fit another frame. I can't keep doing this anymore, and that's when we get our sad face, maximum call stack size exceeded, too much recursion. So this is a bummer, right? Because I can't run this cool recursive intuitive code that I wrote. So wouldn't it be great? Wouldn't we just love to be able to write a recursive function that can recurse as long as it wants, because recursion should be infinite, like theoretically, without adding stack frames. And this is the idea behind something called tail call optimization. You might have heard of this. This is a feature it's an implementation feature. It's something that a JavaScript or another compiler or engine can put into place to help us execute recursive code in a more performant way. And it does that by letting us reuse the resources that we're using for these stack frames. So we sort of get to recycle stack frames in the case where we don't need to remember anything about all of the previous stack frames that have come before from all of those previous recursive calls. So that means we need to write our recursive functions in a specific way where the recursive call occurs in what's called tail position. This is where we come up with the notion of proper tail calls. You might have heard of that. It was introduced in ES6. And the idea is that if we write our recursive code with the recursive call in tail position, or if we write a tail recursive function, it's another way of saying that, and we have an engine that implements tail call optimization, we can run recursive code without running up against that Stack Overflow problem. So how does that work? All right, well, when we talk about tail recursion, I said that I need my recursive function to be tail recursive in order to take advantage of tail call optimization. The function that we wrote before is not tail recursive. Why is that? What is tail recursion? When I make the recursive call here, it is not the last thing that this function does. The function has to do more work after it makes that recursive call and after that returns. So here I've written it, the recursive call happens on the second to last line, so that's already kind of a warning sign that it's not tail recursive because it's not even on the last line of the function. However, that's not, even if it were, even if I took out that dreams variable and just put it all on the last line, it still wouldn't be tail recursive because this function has to wait for the result of recursive inception n-1 to come back and then do something. In this case, concatenate the string within a dream onto whatever came back from that recursive call. So the function does more work after the recursive call returns, and this means it's not tail recursive. How do we write a tail recursive version of this function? Let's think through it together. So one common pattern to writing tail recursive function is I actually use a helper function to do the recursion so that my outer function, tail recursive inception, is not actually a recursive function. Instead, it has a recursive function inside of it that takes care of the recursion for me. So I've got a helper function called incept, because again, I'm really good at naming things. And I'm just going to call that from my main function, from my outer function, with the input, whatever the n was that I got. Now, in our non-tail recursive version, we were able to kind of remember like how deep we had already gone in our recursive dream dive, thanks to the layering of the stack frames. That kind of remembers like how many within a dreams I still need to go. And in this case, we're not going to do that, so we need some other way of remembering the history, remembering what we've seen already, how far we're already down. So to do that, I'm going to use an accumulator variable, which is going to remember that history that we've seen already. I'm going to call it dreams. And now, in our inner function, when we hit our base case, we're just going to return whatever is in the accumulator. We're not going to do anything else to it. And in our recursive case, we're going to call our incept function. We're going to decrement n. We're going to add another within a dream to our accumulated dreams so far. And then we just we keep going with the recursion until we hit our base case. Now, when I start out the function, when I begin this recursive process, I'm going to pass in our base case as the initial value of the accumulator to kind of start things running. So now, the recursive call here inside incept is in tail position. Why? Because this function does nothing else after that recursive call comes back. It's the last thing it does. All it's going to do is take that result and return it right away. There's no other work to do. So now, I've got my tail recursive inception function. What happens when I run it if I have a tail call optimized JavaScript engine? All right, so I run tail recursive inception with input 3. I've got my stack. I have this frame for my tail recursive inception function, and this calls, all it does is call my incept function. So now I get a new frame for the first call to incept, which has n is 3, and the accumulator, I'm going to start out with that base case, a dream. That's going to make a recursive call to incept of 2 with a slightly longer accumulator, because we've added on one layer of dreams. And so I get a new stack frame for my call to incept of 2. But now here's the thing, whenever this call to incept of 2 returns, the frame, the calling context from the incept of 3 call is just going to return that result immediately to whatever called it. So I don't actually need to remember anything about what's going on here anymore in our incept of 3 call. So I can take that frame and I can throw it out. I don't need it anymore. Or better yet, since we're eco-friendly, I can recycle it. So maybe I reuse the resources, or maybe we just like get rid of it and now I have room for another one. But in any case, I can just get rid of it. So now my stack has been elided. It's been kind of shortened. We've taken out the middle step because whenever this returns, I can just return it straight to the lower stack frame. And so now this makes another call to incept of 1. We get a new stack frame from that. Same as before, we can take this one. I don't need it anymore. I can recycle it. Boom, gone. This is going to make a call to incept of 0. Same thing, I can recycle my incept of 1 frame, boom, gone. And now my incept of 0 has hit my base case, so it's just going to return back. And I'm going to get my output, a dream within a dream within a dream. Within a dream. Wow, that's hard to keep track of. Anyway, the point being that now what we've done, we've executed this recursive code, but with a constant number of stack frames. We haven't had to add on stack frames for every recursive call. So this means now, if I have my code written recursively, for me as a human, that's great because it's more intuitive for me, but the computer can execute it in a more iterative fashion. It's almost like JavaScript sees this as a for loop, where it's like, okay, start out with n being 3 and the accumulator being a dream, and then as n goes to 0, just keep adding phrases to the dream's accumulator and keep decrementing n until we hit 0, and then just log it. Just tell me what it is. So we've got code that's written recursively, that's executed a little bit more iteratively, and is therefore more machine efficient. It allows us to go to much, much greater depths of recursion, or infinite, possibly, recursion, without ever hitting that Stack Overflow. So, all right, I've wrapped my little tail-recursive inception function in a little script so I can run it, so I'm getting really excited. Anjana told me that we can run this, and we can get 30,000 different nested withins, and they're not going to fit on the slide, but let's try it. All right, ready? Go! Oh. I got another Stack Overflow. Lies! Betrayal! I told you that this would work, and it did not work. What is going on? My heart is broken. So remember how I said that tail call optimization was a feature of some JavaScript engines? Asterisk? Yeah, that's a pretty big asterisk. Really, only a couple have implemented this. Most do not. So WebKit has it, so Safari has it, and V8, powering Chrome and Node, had it, but then removed it. And that's because this is kind of a hotly debated feature. Basically, there are some disadvantages to doing tail call optimization. Like, for example, since I'm messing with the stack, debugging could theoretically be a little bit harder because we don't have the complete stack trace that accurately reflects what I actually did, because we're messing with what that stack process, what the sequence of stack frames was. So some people argue it makes debugging a little bit harder. And in any case, there's a lot of discussion. It continues, it's ongoing. There's discussion about, there's a great blog post from the V8 team about why they took it out, or what the problems are. And there's also ongoing discussions of how to do this better, how to solve those problems. There's a proposal for putting this in WebAssembly. So anyway, this is it's a thing we all need to work on. But there are ways to access that tail call optimized version of these engines. So in Node, for example, if I go back to Node 6, I'm going to use NVM to switch over to 6, and if I use the flag Harmony tail calls, or just Harmony, now I claim that if I do this, I'm accessing the tail call optimized version of this JavaScript engine, and so if I run this, I get 30,000 withins. It takes it a minute, but it comes back. It doesn't fit on the slide, but you get the idea, and you can try it out at home if you don't believe me. And so yay! I wrote code recursively, and thanks to my very difficult to get at, but it's there, tail call optimized JavaScript engine, I'm able to do this recursion without blowing the stack, thanks to the tail call optimization feature, which allows us to recycle resources, recycle stack frames, so we can use a constant number of stack frames for any depth of recursion. Okay, so this also makes my heart warm and fuzzy, because what we've just done is we've taken loving features from JavaScript and from the teams that have implemented tail call optimization in our JavaScript engines, and we've taken the kind of model of recursion, of iteration, of looping and executing code repetitively while changing the state of things, to allow us to execute our recursive code in a more machine-efficient way. So again, warm fuzzies. I think that this shows that we've got iteration on one hand and recursion on the other hand, but it doesn't have to be a versus situation. It doesn't have to be this Capulets and Montagues, pew pew pew, everybody, Instead, we can actually unite them with a little love from JavaScript. We've been able to take elements of one and bring them into the other to make them both easier to work with. in terms of human efficiency and in terms of machine efficiency. So this gives us now two options that we can use. We can decide as programmers which one is a better fit for our particular problem, and they're more accessible to us because we don't have those problems of not being able to do it human efficiently or not being able to do it machine efficiently. So we've got the choice. And I think as programmers and as a community, when we're trying to advance the state of programming, this is what we should be aiming for. We should be aiming to add more options, more tools to our toolbox. Give us more possibilities for choosing the right paradigm, the right mental model for the problem that we're trying to solve. So, if you're curious about this, if you want to dig in, there's some links on the slides, and I'll post these on Twitter. And yeah, that's my talk. Dziękuję. I want to thank the organizers so much. And if you want to get in touch with me, you can find me on Twitter or at Anjana@mapbox.com. Thanks so much.